Tonight, we're going to talk about something that's going to change everything you thought you knew about the moon. For decades, we've been told the moon is inactive, a lifeless rock floating in space, completely static, nothing more than a frozen museum of the early solar system. Scientists called it a dead world because nothing interesting happens there anymore. No volcanoes, no earthquakes, no atmosphere, no water, just ancient craters and dust that's been sitting unchanged for billions of years. But here's what's actually happening right now, and this is going to sound impossible. The moon is flashing. It's shrinking. It's shaking. It's releasing gas. And we have no idea why some of this is happening. By the end of tonight, you're going to understand that the moon we thought we knew doesn't exist. The real moon, the one actually orbiting Earth right now, is far stranger and more active than anyone imagined. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something that sounds impossible, but is actually documented fact. The moon flashes. Not metaphorically, not in some abstract sense. The lunar surface actually produces temporary flashes of light that appear and disappear within seconds or minutes. Astronomers have been observing these mysterious lights for centuries, and we still don't have a complete explanation for what causes them. These events are called Transient Lunar Phenomena, or TLPs. The name sounds technical and sterile, but what it describes is genuinely bizarre. Temporary changes in the moon's appearance that happen and then vanish. Flashes of light, glowing spots, color changes, obscurations, where part of the surface suddenly becomes harder to see. These aren't subtle effects that require sophisticated instruments to detect. Many TLPs are visible through ordinary telescopes. Some have even been seen with the naked eye by observers who knew exactly where to look. The first documented observation of a TLP happened in November of 1787. William Herschel, the astronomer who discovered Uranus, was observing the moon through his telescope when he noticed something extraordinary. He saw what he described as red glowing spots on the lunar surface, specifically in the dark areas not illuminated by the sun. Herschel was not a casual observer or someone prone to making things up. He was one of the most respected astronomers of his time, meticulous in his observations and careful in his conclusions. He documented what he saw, noting the location and appearance of these glowing spots. At the time, he speculated they might be lunar volcanoes actively erupting. That explanation made sense, given what scientists knew in the late 1700s. If Earth had active volcanoes, why wouldn't the moon? But as our understanding of the moon improved over the following century, that explanation became problematic. The moon appeared to be geologically dead. No volcanic activity had been detected in modern times. The idea that Herschel had witnessed an actual volcanic eruption seemed increasingly unlikely. But the observations didn't stop. Throughout the 1800s and 1900s, astronomers continued to report strange, temporary phenomena on the lunar surface. In November of 1958, Russian astronomer Nikolai Kozyrev was observing the crater Alphonsus when he detected a reddish glow near the crater's central peak. He immediately took a spectrogram, a scientific measurement that breaks light into its component colors to identify what's emitting that light. The spectrum showed emission lines consistent with molecular carbon, suggesting some kind of gas release or outgassing event. This was remarkable because it provided actual scientific data, not just a visual observation. Something on the moon had released gas that glowed briefly, then disappeared. The Apollo astronauts reported TLPs as well. These were trained observers, pilots and engineers, not people prone to flights of fancy. During the Apollo 17 mission in December of 1972, astronauts Eugene Cernan and Harrison Schmitt reported seeing strange glows on the lunar horizon. They described flashes and light phenomena that they couldn't easily explain. These observations were made while they were on the lunar surface, with their own eyes, in spacesuits, standing on the moon itself. Whatever they saw was real enough to document and report back to mission control. One of the most active locations for TLPs is a crater called Aristarchus. This crater sits in a region called Oceanus Procellarum on the moon's near side, easily visible from Earth. Aristarchus is bright, one of the most reflective features on the lunar surface, and it's been the site of hundreds of reported TLP observations over the years. Observers have reported reddish glows, bluish tinges, temporary brightenings, obscurations, where the crater, temporarily, becomes harder to see through the haze. These events happen at Aristarchus far more frequently than at other locations on the moon. Nobody knows exactly why Aristarchus is such a hotspot for TLPs. Some researchers think it might be related to the geology of the region. Aristarchus sits at the edge of a large volcanic plain, and there might be ongoing gas releases from beneath the surface. Or it could be related to the fresh, bright material that makes up the crater walls, which might respond differently to solar radiation or particle bombardment. Modern astronomers have set up automated monitoring systems to watch for TLPs. Telescopes, equipped with cameras, continuously photograph the moon, and software analyzes the images, looking for temporary changes in brightness or color. These systems have detected numerous TLP events, confirming that the phenomena are real and ongoing. One systematic study documented over 300 TLP events between 1950 and 1999. That's an average of 6 events per year that were significant enough to be recorded and verified. The actual number of TLPs is probably much higher because most of the lunar surface isn't under continuous observation. Think about what that means. At any given moment, only a tiny fraction of the moon's surface is being watched by telescopes sensitive enough to detect TLPs. Most amateur astronomers don't even know what TLPs are, so they're not looking for them. Professional observatories are usually focused on other targets, distant galaxies or exoplanets or other astronomical objects far beyond our solar system. The moon is right here, close and familiar, so it doesn't get constant attention. But when observers do watch the moon systematically, looking specifically for temporary changes, they find them. The 300 documented events are just the tip of the iceberg. The actual rate of TLPs could be dozens per year, possibly even more. And that raises an uncomfortable question. If the moon is constantly producing these mysterious flashes and glows, why didn't we notice sooner? Why did it take centuries of observations before scientists took TLPs seriously? Part of the answer is skepticism. For much of the 20th century, astronomers dismissed TLP reports as observational errors. Maybe the observer's telescope had a smudge on the lens. Maybe atmospheric turbulence created the appearance of a flash. Maybe it was an optical illusion, a trick of the eye. Professional astronomers, trained to be skeptical and to demand rigorous evidence, often didn't believe the reports. It wasn't until the Kozyrev observation in 1958, with its spectroscopic confirmation, that the scientific community started taking TLPs seriously. Here was objective, measurable data, not just a subjective visual observation. The spectrum showed emission lines, proof that something physical had happened. Even then, acceptance was slow. Many astronomers remained unconvinced, arguing that Kozyrev's observation could have been contaminated by some instrumental artifact. But as more and more reports accumulated, from more and more independent observers using different telescopes and different techniques, the evidence became impossible to ignore. TLPs were real. Something was causing temporary changes in the moon's appearance. The question shifted from whether TLPs exist to what causes them. So what causes these mysterious flashes and glows? Several mechanisms have been proposed, but none fully explains all the observations. One possibility is outgassing. The moon's interior might still contain pockets of volatile materials, gases trapped beneath the surface. If these gases escape through cracks or fissures, they could create temporary glows as they interact with solar radiation or get ionized by the sun's ultraviolet light. This would explain the spectroscopic detection of carbon that Kozyrev observed. Gas molecules escaping from the moon and briefly glowing before dispersing into space. Another possibility is meteorite impacts. The moon is constantly being bombarded by small meteorites, most too small to create lasting craters, but large enough to create brief flashes of light when they hit. The impact vaporizes a tiny amount of surface material, creating a momentary glow. NASA's Lunar Reconnaissance Orbiter has actually photographed fresh impact craters on the moon, some only tens of feet across, formed between different imaging passes. These impacts are common. Estimates suggest the moon gets hit by several hundred small meteorites every year that are large enough to create detectable flashes. NASA even runs a program specifically dedicated to monitoring these impact flashes. The Meteoroid Environment Office at Marshall Space Flight Center operates telescopes that watch the moon's dark side, the part not illuminated by the sun, looking for brief flashes. When a meteorite hits the moon at tens of thousands of miles per hour, the kinetic energy of the impact is enormous. The meteorite and a small amount of lunar surface material instantly vaporize, reaching temperatures of thousands of degrees. This creates a brief, intense flash of light visible from Earth. The flash typically lasts only a fraction of a second, much shorter than most reported TLPs. Since 2005, NASA's monitoring program has detected hundreds of these impact flashes. Most are faint, requiring sensitive equipment to detect. Some are bright enough to be visible through amateur telescopes, if you happen to be watching the right spot at the right time. The brightest impact flash ever recorded happened in March of 2013. A meteorite, estimated to weigh about 90 pounds, hit the moon traveling at approximately 56,000 miles per hour. The impact released energy equivalent to 5 tons of TNT and created a flash so bright it was visible to the naked eye for about 1 second. The crater it formed is probably about 65 feet across. This event proved that meteorite impacts can definitely create flashes visible from Earth. But meteorite impacts don't explain all TLP observations, especially the ones that last minutes or hours rather than seconds, or the ones that recur at the same locations. A meteorite impact is a random event. It can happen anywhere on the moon at any time. There's no reason for impacts to cluster in specific locations like Aristarchus. And impact flashes are white or yellowish, the color of hot vaporized rock. But some TLP observations describe reddish or bluish glows, colors that don't match impact flash spectra. So while meteorite impacts explain some observations, They can't explain all of them. There must be other mechanisms at work. But meteorite impacts don't explain all TLP observations, especially the ones that last minutes or hours rather than seconds, or the ones that recur at the same locations. A third possibility involves electrostatic phenomena. The Moon has no global magnetic field and no atmosphere, so the surface is directly exposed to the solar wind, a stream of charged particles flowing from the Sun. These particles can charge up lunar dust, causing it to levitate temporarily off the surface. This electrostatically levitated dust could scatter sunlight in strange ways, creating temporary glows or obscurations. This mechanism has been demonstrated in laboratory experiments where lunar soil simulant was exposed to charged particle beams. The dust grains acquired electric charge and lifted off the surface, creating a temporary cloud. If this happens on the Moon, it could explain some TLPs, especially the obscurations where parts of the surface become temporarily hazy. But here's the thing. None of these explanations accounts for all observed TLPs. Some events seem too bright or too long-lasting to be simple meteorite impacts. Some occur at locations and times that don't correlate well with expected outgassing or electrostatic activity. Some show spectral features that don't match any of the proposed mechanisms. After centuries of observations and decades of scientific investigation, we still don't have a complete understanding of what's happening. The Moon, supposedly a dead and unchanging world, is producing light phenomena that we can't fully explain. That's unsettling because the Moon is literally the closest celestial body to Earth. It's only about 240,000 miles away. We've sent 12 humans to walk on its surface. We've orbited it dozens of times. We've mapped it in extraordinary detail. And yet it's still doing things we don't understand. The TLP mystery reminds us that even familiar objects in our cosmic neighborhood can surprise us. The Moon we thought we knew, the dead, boring, unchanging Moon of textbooks, isn't the real Moon. The real Moon flashes and glows for reasons we're still working to understand. And that's just the beginning of the strangeness. While the Moon is flashing, it's also shrinking. Not rapidly, not catastrophically, but measurably and continuously. The Moon is getting smaller, and this discovery has profound implications for our understanding of what's happening beneath that dusty grey surface. For most of human history, we assumed the Moon's size was fixed. Why wouldn't it be? It's a solid rock. Rocks don't shrink. But in the early 21st century, NASA's Lunar Reconnaissance Orbiter, or LRO, started photographing the Moon's surface in unprecedented detail. LRO carries cameras capable of imaging features as small as 1.5 feet across from orbit. That's roughly the size of a large piece of furniture. From orbit around the Moon, this spacecraft can see individual boulders sitting on the surface. And what LRO found was stunning. The lunar surface is covered with thousands of relatively young scarps, basically cliffs or ridges, where one section of the surface has been pushed up and over another section. These features are called thrust faults, and they form when the ground is being compressed, squeezed together by tectonic forces. Think of pushing on a rug from both sides. The rug bunches up in the middle, creating wrinkles and folds. That's essentially what's happening on the Moon's surface. The crust is being compressed, and it's responding by buckling and folding, creating these scarps. The LRO images revealed that these thrust fault scarps are everywhere. They range in size from small features a few feet high to massive scarps that stretch for miles and rise tens of feet above the surrounding terrain. The scarps cut across craters, ejector fields, and other surface features, which tells us they formed after those features existed. And here's the crucial detail. These scarps are geologically young. Not young in human terms, but young in lunar terms. To understand what this means, we need to think about geological timescales. The Moon formed roughly 4.5 billion years ago. That's 4,500 million years. A million years, which seems incredibly long to us, is only about 0.02% of the Moon's total age. It's a tiny fraction, essentially nothing in geological terms. When geologists say something is young, they mean it formed recently compared to the age of the planet or Moon. Most lunar features are ancient. The large impact basins, the maria filled with solidified lava, the heavily cratered highlands, these features are billions of years old. They formed early in the Moon's history, when the solar system was violent and chaotic, when giant asteroids were still common and volcanic activity was vigorous. Since then, for roughly the last 3 billion years, the Moon has been relatively quiet. Impact rates dropped dramatically after the period called the Late Heavy Bombardment, which ended about 3.8 billion years ago. Volcanic activity ceased around 3 billion years ago, maybe a bit more recently in some areas. The assumption was that the Moon had been essentially frozen in time since then, just sitting there accumulating the occasional impact crater, but otherwise unchanged. The thrust fault scarps discovered by LRO contradict this assumption. These scarps appear to be less than 50 million years old. Some might be even younger, possibly forming within the last few million years. To determine the age of a surface feature on the Moon, scientists count impact craters. This technique, called crater counting, is based on a simple principle. The longer a surface has been exposed, the more time it's had to accumulate impact craters. An old surface will be heavily cratered. A young surface will have few craters. By counting the number of craters of different sizes and comparing that distribution to models of how cratering rates have changed over time, scientists can estimate when the surface formed. The thrust fault scarps have very few craters on them. In some cases, they have almost no craters at all. This tells us they formed recently. If they'd been there for billions of years, they'd be covered with impact craters, just like the surrounding terrain. But they're not. They're relatively pristine, meaning they're young. Some of the scarps actually cut through small craters, meaning the scarp formed after the crater. You can see the sequence of events in the images. First, a small asteroid hit the Moon, creating a crater. Then, much later, the ground shifted as the Moon shrank, creating a thrust fault that disrupted the crater. The fault is younger than the crater. By dating the crater, you can establish a maximum age for the fault. It has to be younger than whatever it cuts through. The Moon is roughly 4.5 billion years old. Most of its surface features, the big craters and maria, are billions of years old, formed early in the Moon's history. But these thrust fault scarps appear to be less than 50 million years old. Some might be even younger, possibly forming within the last few million years. That's essentially yesterday, in geological terms. The Moon is still tectonically active right now, today, in the 21st century. So why is the Moon shrinking? The answer lies in its interior. The Moon, like Earth, was born hot. When it formed about 4.5 billion years ago, probably from the debris of a giant impact between Earth and a Mars-sized object, it was molten. A ball of liquid rock glowing red-hot in space. Over billions of years, the moon has been slowly cooling down, radiating its internal heat into the coldness of space. As the interior cools, it contracts. Molten or hot rock takes up more space than cool, solid rock. When the moon's interior cools and solidifies, it occupies less volume, and the whole moon shrinks. This process is ongoing. The moon is still losing heat, still cooling, still contracting. Scientists estimate that the moon has shrunk by about 160 feet in radius over the past few 100 million years. That might not sound like much. 160 feet is roughly the length of half a football field. But when you're talking about an object that's 1,700 miles in radius, that shrinkage represents an enormous amount of stress on the crust. The crust is rigid, made of solid rock, and it doesn't compress easily. So, when the interior contracts, pulling the crust inward, the crust responds by breaking and folding. That's what creates the thrust fault scarps. One section of crust gets pushed up and over the adjacent section, relieving the compressive stress. This is similar to what happens on Earth, but there's a key difference. Earth is geologically active in a different way. Earth has plate tectonics, with crustal plates moving around, colliding, subducting, creating mountains and ocean trenches. Earth's surface is constantly being recycled and renewed. The moon doesn't have plate tectonics. Its crust is a single solid shell, and the only way it can respond to internal stresses is by fracturing and folding. That's exactly what we see in the LRO images. The discovery of these young thrust faults changed our understanding of the moon fundamentally. Before LRO, most scientists believed the moon had been geologically dead for billions of years. The Maria, those dark plains you can see from Earth, are ancient lava flows that erupted roughly 3 to 4 billion years ago and then stopped. Since then, the thinking went, nothing much has happened. The moon just sat there, a cold, dead rock, occasionally getting hit by meteorites, but otherwise unchanging. LRO proved that assumption wrong. The moon is still active, still changing, still responding to internal processes. The rate of change is slow by human standards, but it's real and ongoing. This has practical implications for future lunar exploration. NASA and other space agencies are planning to establish permanent bases on the moon within the next couple of decades. Astronauts will live and work on the lunar surface for extended periods. Those bases need to be built in safe locations. If a large thrust fault scarp suddenly formed beneath a lunar base, it could destroy habitats and infrastructure. The ground could rupture, buildings could collapse, equipment could be damaged. So mission planners are using LRO data to map the locations of existing faults and to identify areas that appear tectonically stable. The goal is to place future bases in regions where the risk of surface rupture is minimized. There's something deeply fascinating about the idea that the moon is still evolving, still changing shape, still adjusting to its own cooling. We tend to think of astronomical objects as static, unchanging on human timescales. The moon looks the same tonight as it did when your great-great-grandparents looked up at it. But on longer timescales, the moon is dynamic. Its surface is being reshaped by ongoing tectonic processes. The scarps forming today are features that will be visible for millions of years, permanent records of the moon's gradual contraction. And as we'll see, this shrinking process doesn't just create surface scarps. It also causes the moon to shake, producing seismic activity that shouldn't exist on a supposedly dead world. Now, let's talk about one of the most surprising discoveries ever made about the moon: water. For decades, scientists were absolutely certain that the moon was completely dry, not just lacking oceans or lakes, but devoid of water molecules altogether. The moon was thought to be one of the driest places in the solar system, a desiccated ball of rock where water couldn't exist in any form. Every textbook, every research paper, every scientific discussion about the moon assumed this as a basic fact. The moon has no atmosphere, so liquid water can't exist on the surface because it would immediately evaporate into space. The moon's surface gets extremely hot during the lunar day, reaching temperatures around 250 degrees Fahrenheit in direct sunlight. Any water molecules on the surface would be quickly broken apart by solar ultraviolet radiation or simply heated until they escaped into space. The Apollo astronauts who brought back lunar soil samples found no water in those samples. The rocks appeared bone dry, completely devoid of even trace amounts of water. Chemical analyses confirmed it. The moon was waterless. This made sense given the moon's formation. If the moon formed from a giant impact, as most scientists believe, the collision would have been so violent and so hot that any volatile materials, including water, would have been vaporized and lost to space. What condensed back into the moon would be depleted in volatiles, including water. But in the early 21st century, this certainty started to crack. The first hint came from orbital missions. In 2008, India's Chandrayaan-1 spacecraft was orbiting the moon, carrying an instrument called the Moon Mineralogy Mapper. This instrument analyzed sunlight reflected off the lunar surface, looking at specific wavelengths to identify what minerals were present. And it detected a signature of water molecules and hydroxyl groups at high latitudes on the moon. Not liquid water, not ice that you could see, but water molecules bonded to minerals in the lunar soil. This was shocking. The signal was weak, suggesting only trace amounts of water, but it was definitely there. The moon was not bone dry after all. Initially, some scientists were skeptical. Maybe the instrument was detecting contamination from Earth's atmosphere or from the spacecraft itself, but other missions confirmed the finding. NASA's Deep Impact spacecraft, which had previously visited a comet, turned its instruments toward the moon and detected the same water signatures. The Cassini spacecraft, on its way to Saturn, flew past the moon and also detected water signatures. Multiple, independent observations, all pointing to the same conclusion. The moon has water molecules on its surface. Then, in 2009, a NASA mission called LCROSS did something dramatic. LC-ROSS, which stands for Lunar Crater Observation and Sensing Satellite, deliberately crashed a spent rocket stage into a permanently shadowed crater near the moon's south pole. The impact kicked up a plume of debris, and instruments on the LC-ROSS spacecraft analyzed that plume before the spacecraft itself crashed into the moon. And what they found was water ice. Not just trace amounts, but significant quantities. The plume contained water vapor, water ice crystals, and other volatile compounds. The permanently shadowed craters at the moon's poles, where temperatures never rise above about -250 degrees Fahrenheit, act as cold traps. Any water molecules that wander into these regions freeze and get stuck there, unable to escape because it's too cold for them to evaporate. Over billions of years, these cold traps have accumulated substantial amounts of water ice. Estimates suggest there could be hundreds of millions of tons of water ice in the permanently shadowed regions of the moon. That's a lot of water. It's still small compared to Earth's oceans, but it's far more than anyone expected to find on the supposedly dry moon. Then, in 2020, another discovery pushed the boundaries even further. NASA's SOFIA telescope, which is actually a modified Boeing 747 aircraft carrying a large infrared telescope, made observations of the moon's sunlit surface. SOFIA detected water molecules on the sunlit parts of the moon, not just in the permanently shadowed cold traps. This was even more surprising. How could water molecules survive on the sunlit surface where temperatures are hot enough to boil water? The answer seems to be that the water is somehow protected, possibly trapped inside tiny glass beads formed during meteorite impacts, or bonded to minerals in a way that shields it from direct solar radiation. The water molecules might also be constantly being replenished. The solar wind, that stream of charged particles flowing from the sun, contains hydrogen. When hydrogen from the solar wind hits oxygen in lunar minerals, it can form water molecules. This process might be continuously creating small amounts of water on the lunar surface, even as existing water is being destroyed by radiation. It's a dynamic process, with water molecules being created and destroyed constantly, maintaining a low but detectable abundance. This discovery of water on the moon changes everything for future lunar exploration. Water is incredibly valuable in space. Astronauts need water to drink, about 1 gallon per person per day for drinking and food preparation, plus more for hygiene and other uses. Carrying all that water from Earth is expensive. Every pound of payload costs thousands of dollars to launch into space. The exact cost depends on the rocket and mission, but as a rough estimate, it costs about $10,000 to launch 1 pound of payload to the moon. A gallon of water weighs about 8 pounds. So every gallon of water costs roughly $80,000 to transport from Earth to the moon. For a crew of 4 astronauts staying on the moon for a month, you'd need at minimum about 120 gallons of drinking water alone. That's nearly $10 million just for drinking water, not counting water for hygiene, growing food, or industrial processes. If astronauts can extract water from the moon itself, that dramatically reduces the cost and complexity of long-term missions. Instead of launching massive quantities of water from Earth, you launch equipment to mine and purify lunar water. The equipment is heavy and expensive to launch, but once it's on the moon, it can produce water indefinitely from local resources. This is the principle of in situ resource utilization, or ISRU. Use what's available locally rather than bringing everything from home. It's the same principle that allowed early explorers and settlers on Earth to survive. They hunted local animals, gathered local plants, and used local materials to build shelter. They didn't carry everything they needed from their home countries. If we're going to establish a permanent presence on the moon, we need to apply the same principle. Use lunar resources to support lunar operations. Water can also be split into hydrogen and oxygen through electrolysis. You run an electric current through water, and it breaks apart into hydrogen gas and oxygen gas. Oxygen is necessary for breathing. On Earth, we take oxygen for granted. It's everywhere, making up about 21% of our atmosphere. On the moon, there's no breathable atmosphere. Astronauts need to bring their own oxygen or produce it locally. Splitting lunar water gives you oxygen to breathe, and both hydrogen and oxygen can be used as rocket fuel. This is not some futuristic speculation. Hydrogen and oxygen are already used as rocket fuel right here on Earth. The space shuttle's main engines burned liquid hydrogen and liquid oxygen. The upper stages of many rockets use the same propellants. When hydrogen and oxygen combine in a rocket engine, they produce water vapor and release enormous amounts of energy. It's an extremely efficient and powerful combination. If you can produce hydrogen and oxygen on the moon, you can refuel spacecraft there. A spacecraft traveling from Earth to Mars could stop at the moon, refuel using locally produced propellants, and then continue to Mars with full tanks. This makes the moon potentially a refueling station for deep space exploration. Instead of launching everything you need from Earth's surface, which requires fighting Earth's strong gravity, you launch from the moon's surface, where gravity is only 1/6 as strong. It takes far less energy to launch from the moon than from Earth. So the strategy becomes, get to the moon, refuel using lunar water, and then launch from the moon to your final destination. You save enormous amounts of energy and mass. This concept is sometimes called a lunar gateway or a cislunar depot. The moon becomes a strategic location in space transportation infrastructure, not just a destination, but a waypoint. The presence of water also raises new scientific questions that go beyond practical applications. Where did this water come from? How did it get there? How much is there? These questions matter because they tell us about the moon's history and about the early solar system. Some of the lunar water might have been delivered by comets and asteroids that crashed into the moon over billions of years. Comets are essentially dirty snowballs, mixtures of ice and rock. When a comet hits the moon, it vaporizes on impact. But some of the water vapor might condense in cold regions and get trapped. Over 4 billion years of impacts, this process could accumulate significant amounts of water ice in permanently shadowed craters. Some water might have been trapped during the moon's formation. If the giant impact that created the moon involved materials that contained some water, and if those materials ended up in regions that never got hot enough to drive the water off, then primordial water might still exist on the moon. This would be water from the very beginning, from the birth of the Earth-Moon system. Some water might be actively being created by the solar wind. This is the most surprising possibility. The solar wind is a stream of particles flowing from the sun, mostly protons and electrons, but also helium nuclei and trace amounts of heavier elements. When a proton from the solar wind hits an oxygen atom in a lunar mineral, they can combine to form a hydroxyl group, OH. Two hydroxyl groups can then combine to form a water molecule, H2O. This process, called solar wind implantation, might be continuously creating small amounts of water on the moon's surface. The water is then destroyed by solar ultraviolet radiation or by subsequent impacts, but new water is always being created to replace it. It's a dynamic equilibrium, with creation and destruction balanced. If this process is happening, it means the moon is manufacturing its own water right now, as you read this, not in large quantities, but enough to maintain the trace amounts detected on the sunlit surface. Understanding which of these sources is most important tells us about the moon's history and about processes happening throughout the solar system. Understanding the sources and distribution of lunar water is now a major research priority. Multiple countries and private companies are planning missions to land near the lunar poles, drill into the permanently shadowed regions, and analyze the ice deposits there. China's Chang'e missions have been exploring the moon's polar regions. NASA's Artemis program plans to land astronauts near the South Pole, where the water ice is abundant. Private companies like Astrobotic and Intuitive Machines are developing lunar landers specifically designed to prospect for water. The moon we thought we knew was a dry, sterile rock with nothing to offer future explorers except a place to plant a flag. The moon we've actually discovered is a world with resources, with water that can sustain human presence and enable further exploration. That's a fundamental shift in how we think about the moon's potential. A dead world with no resources isn't worth visiting except for science and prestige. A world with accessible water becomes a strategic location, a stepping stone to the rest of the solar system. And as we'll see next, the discovery that the moon is more active than expected extends beyond just its surface features. The moon's interior is also producing phenomena that challenge our understanding of what a small, supposedly dead world should be doing. Let's talk about something that shouldn't be possible. The moon has earthquakes. Except they're not earthquakes, they're moonquakes. And they reveal something profound about what's happening deep inside a world we thought was geologically dead. When the Apollo astronauts visited the moon between 1969 and 1972, they didn't just collect rocks and take photographs. They deployed scientific instruments, and some of those instruments were seismometers. Seismometers detect vibrations in the ground, the same instruments used on Earth to detect and study earthquakes. 4 Apollo missions, Apollo 12, 14, 15, and 16, each placed a seismometer package on the lunar surface at different locations. These instruments operated for years after the astronauts left, continuously monitoring the moon's seismic activity and transmitting data back to Earth. The Apollo seismic network operated from 1969 until it was shut down in 1977. During those 8 years, the instruments detected thousands of seismic events. Not the occasional rumble, but thousands of distinct moonquakes. The exact number depends on how you count them. Some events are clear and distinct, producing sharp signals that are easy to identify. Others are weak and ambiguous, barely above the background noise. But even being conservative, the Apollo seismometers detected several thousand moonquakes during their operational period. That was unexpected. Before Apollo, most scientists assumed the moon would be seismically quiet. The reasoning seemed sound. Earth has earthquakes because it's geologically active. The planet's interior is hot, with a molten outer core and partially molten mantle. The core temperature is estimated at about 9,000 to 13,000 degrees Fahrenheit. That's hotter than the surface of the sun. This internal heat drives convection in the mantle, the slow churning motion of hot rock rising and cool rock sinking. Convection in the mantle drives plate tectonics, which causes most earthquakes as plates grind past each other or collide. The San Andreas Fault in California marks the boundary between the Pacific Plate and the North American Plate. As these plates slide past each other, stress builds up along the fault. Eventually, the stress exceeds the strength of the rock, and the fault ruptures, producing an earthquake. Earthquakes happen constantly on Earth. Small earthquakes, too weak to feel, occur thousands of times per day. Moderate earthquakes happen dozens of times per week. Major earthquakes, magnitude 7 or higher, happen roughly once per month somewhere on Earth. Earth is seismically active because it's geologically active. The Moon, being much smaller than Earth, should have cooled down billions of years ago. A small object loses heat faster than a large one because it has more surface area relative to its volume. This is basic physics, the same reason a small potato cools faster than a large roast coming out of the oven. Heat escapes through the surface. If you have a lot of volume but relatively little surface area, you retain heat well. If you have a lot of surface area relative to your volume, you lose heat quickly. The Moon's radius is about 1,080 miles, compared to Earth's roughly 3,960 miles. The Moon's volume is only about 2% of Earth's volume, but its surface area is about 7% of Earth's surface area. So the Moon has much more surface area per unit volume than Earth does. It should radiate heat away much faster. Based on this simple calculation, the Moon should have lost most of its internal heat within the first billion years of its existence. A cold interior means no mantle convection, no plate tectonics, no volcanic activity, and therefore no seismic activity. The Moon should be seismically dead, as quiet as a tomb, but it's not. The seismometers deployed by Apollo 12, 14, 15, and 16 proved otherwise. These instruments were remarkably sensitive for their time. They could detect ground motions of less than 1 nanometer at certain frequencies. A nanometer is 1/1000th of a meter, roughly the width of 10 atoms placed side by side. The seismometers could detect vibrations so tiny that they were smaller than atoms. This incredible sensitivity was necessary because moonquakes are generally much weaker than earthquakes. The strongest shallow moonquake ever detected by Apollo was about magnitude 5.5 on the Richter scale. That would be a moderate earthquake on Earth, strong enough to cause damage to buildings, but not catastrophic. Most moonquakes are much weaker, magnitude 2 or 3, barely perceptible. The seismometers sat on the lunar surface for years, continuously monitoring ground vibrations. Every time the ground moved, even slightly, the instruments recorded it. The data was transmitted back to Earth via radio, received by NASA's Deep Space Network and archived for analysis. Scientists spent decades analyzing this data, identifying different types of seismic events, mapping their locations, and trying to understand what they revealed about the Moon's interior. The data is still being analyzed today. Modern computer techniques allow scientists to extract more information from the Apollo seismic data than was possible in the 1970s. New discoveries are still being made from data that's over 50 years old. But it's not. The Apollo seismometers detected 4 distinct types of moonquakes, each revealing something different about the Moon's interior and activity. First, there are thermal moonquakes. These are the most common type, occurring regularly and predictably. They're caused by the extreme temperature changes on the lunar surface. During the lunar day, which lasts about 14 Earth days, the surface temperature rises to around 250 degrees Fahrenheit. During the lunar night, another 14 Earth days, the surface temperature drops to about negative 250 degrees Fahrenheit. That's a temperature swing of 500 degrees Fahrenheit. When rock heats up, it expands. When it cools down, it contracts. These expansion and contraction cycles create stress in the rock, and eventually, the rock fractures, producing a small seismic event. Thermal moonquakes are relatively weak and shallow, occurring in the top few miles of the lunar crust. They don't tell us much about the Moon's deep interior, but they confirm that the lunar surface is under constant stress from temperature changes. Second, there are impact moonquakes. These are exactly what they sound like: seismic signals generated when meteorites crash into the Moon. The Apollo seismometers detected dozens of meteorite impacts during their operational years. Most were small objects, but even a small impact releases significant energy when it hits at tens of thousands of miles per hour. The seismic waves from these impacts travel through the Moon's interior and can be detected by seismometers thousands of miles away. By analyzing how long it takes seismic waves to travel from the impact site to the seismometers, scientists can learn about the moon's internal structure. Different materials transmit seismic waves at different speeds, so the travel time tells you what the waves passed through. Impact moonquakes confirmed what scientists suspected. The moon has a layered structure with a crust, mantle, and small core, similar to Earth, but with different proportions and compositions. Third, and this is where it gets really interesting, there are shallow moonquakes. These occur in the lunar crust, typically at depths between 12 and 60 miles below the surface. Shallow moonquakes are much stronger than thermal moonquakes, sometimes reaching magnitudes between 5 and 6 on the Richter scale. An earthquake of that magnitude on Earth would cause significant damage to buildings. On the moon, where there are no buildings except the ones we've put there, these quakes shake the ground violently. Shallow moonquakes appear to be related to the tectonic stresses we discussed earlier. The moon is shrinking as its interior cools, creating compressive stress in the crust. Most of the time, this stress is accommodated by the slow formation of thrust fault scarps. But sometimes the stress builds up until it's suddenly released in a fracturing event, a moonquake. The connection between shallow moonquakes and the thrust fault scarps has been confirmed by recent research. Scientists have been able to correlate some moonquake epicenters with the locations of fault scarps imaged by LRO. The quakes are happening along the faults, exactly as you'd expect if the shrinking moon is causing tectonic activity. This means the shallow moonquakes are ongoing evidence of the moon's continued tectonic evolution. They're happening right now, today, as the moon continues to cool and contract. Future astronauts living on the moon will experience these moonquakes. That's one reason mission planners are carefully studying moonquake data to identify the safest locations for lunar bases. But the fourth type of moonquake is the most mysterious and the most surprising, and it tells us more about the moon's interior than any other type of seismic event: deep moonquakes. These occur at depths between about 430 and 620 miles below the lunar surface. To put that in perspective, the moon's radius is about 1,080 miles. So these quakes are happening more than halfway from the surface to the center, deep in the lunar mantle. Deep moonquakes are relatively weak compared to shallow moonquakes, typically around magnitude 2 on the Richter scale. A magnitude 2 earthquake on Earth is so weak that people rarely feel it. You'd need sensitive instruments to detect it. On the moon, where there are no people to feel the ground motion, these weak quakes would go completely unnoticed without seismometers. But here's what makes them remarkable, and why they're so important to understanding the moon. They occur repeatedly at the same locations. This is completely different from thermal moonquakes or impact moonquakes, which happen randomly wherever temperature changes are greatest or wherever meteorites hit. The Apollo Seismic Network identified about 250 distinct deep moonquake source regions. These are specific locations deep in the moon's mantle that produce moonquakes over and over again. It's like the moon has 250 seismic hotspots buried in its interior, and they keep triggering again and again. Each of these regions produces moonquakes periodically, and here's the astonishing part. The timing is linked to the moon's position in its orbit around Earth. This is not random. This is a clear, measurable correlation. Deep moonquakes occur most frequently when the moon is at perigee, the point in its orbit when it's closest to Earth, and at apogee, the point when it's farthest from Earth. The moon's orbit is not a perfect circle. It's an ellipse, slightly elongated. At perigee, the moon is about 225,000 miles from Earth. At apogee, it's about 252,000 miles from Earth. That's a difference of about 27,000 miles, or about 11% variation in distance. This variation in distance changes the strength of tidal forces. When the moon is closer to Earth, Earth's gravity pulls harder on the moon. When the moon is farther away, Earth's gravity pulls less hard. This pattern strongly suggests that deep moonquakes are triggered by tidal stresses, just as the moon's gravity creates tidal bulges in Earth's oceans, raising and lowering sea level by several feet twice a day. Earth's gravity creates tidal stresses inside the moon. The moon has no oceans, obviously, but it has rock, and rock deforms under stress, even solid rock. When Earth's gravity pulls on the moon, the entire moon gets stretched slightly in the direction toward Earth. The side facing Earth bulges outward very slightly, and the opposite side also bulges outward. The middle section gets compressed. These tidal forces are strongest when the moon is closest to or farthest from Earth, because those are the points where the tidal forces change most rapidly as the moon moves through its orbit. Apparently, certain regions deep in the moon's mantle are under stress, sitting right on the edge of failure, and they respond to these tidal triggers by slipping. When the rock slips, it releases stored elastic energy as seismic waves, which is what the seismometers detect as a moonquake. Think of it like a door that's stuck. You push on it gently and nothing happens. The door is jammed, held in place by friction. You push a bit harder, still nothing. Then you give it one more push, just a little bit more force, and suddenly the door breaks free and swings open. That last little push triggered the release, but the door was already under stress and ready to move. The tidal stress from Earth is like that last little push. The rock, deep in the moon's mantle, is already under stress from the moon's cooling and contraction. Most of the time, friction holds it in place. But twice a month, when tidal stresses peak at perigee and apogee, that extra stress is enough to overcome friction, and the rock slips. The fact that this happens at the same locations over and over tells us that these regions haven't fully relaxed. They're still under stress, still accumulating strain, still ready to slip again when the next tidal trigger comes along. But here's the problem, the paradox that puzzled scientists when they first analyzed the Apollo seismic data. Deep moonquakes shouldn't be possible in a cold, completely dead moon. For rock to slip and generate seismic waves at depths of 400 to 600 miles, that rock needs to be warm enough to deform and store elastic energy. If the moon's interior were completely cold and rigid, completely solid throughout, tidal stresses would just compress the rock slightly without causing any quakes. Cold, rigid rock doesn't slip, it just gets squeezed. The fact that deep moonquakes occur tells us something profound. The moon's deep interior is not completely cold. There's still enough residual heat down there to keep the rock in a state where it can deform and fracture rather than just being compressed elastically. This was a major surprise when scientists first realized it. It means the moon's interior is cooling more slowly than expected, more slowly than simple thermal models predicted. Even 4.5 billion years after its formation, even after all this time, the deep mantle retains enough heat to remain partially ductile, warm enough to behave in complex ways, rather than just sitting there frozen solid. This was a major surprise. It means the moon's interior is cooling more slowly than expected. Even 4.5 billion years after its formation, the deep mantle retains enough heat to remain partially ductile. This has implications for our understanding of how small planetary bodies evolve. It suggests that even relatively small objects can retain internal heat for billions of years, especially if they have insulating layers or if radioactive decay continues to generate heat in their interiors. There's another intriguing aspect to deep moonquakes. Some researchers have suggested a connection between deep moonquakes and the transient lunar phenomena we discussed earlier. If deep moonquakes cause fractures that propagate to the surface, they could create pathways for gas to escape from the moon's interior. That escaping gas might produce the glows and flashes observed as TLPs. This is speculative, and the connection hasn't been definitively proven, but it's plausible. Moonquakes could trigger gas releases, and those gas releases could create visible phenomena. If true, it would tie together two of the strangest aspects of lunar activity: the mysterious flashes on the surface and the mysterious quakes deep below. The discovery of moonquakes, especially deep moonquakes, fundamentally changed how scientists view the moon. The moon is not geologically dead. It has ongoing seismic activity driven by its cooling interior and by tidal interactions with Earth. That activity is relatively minor compared to Earth's earthquakes and volcanic eruptions, but it's real and measurable. Future lunar missions are planning to deploy new seismometer networks with more instruments and better sensitivity than the Apollo seismometers. These new networks will help us understand moonquakes in greater detail, map the moon's internal structure more precisely, and potentially identify the safest locations for permanent human settlements. The moon shakes. It's been shaking for billions of years, and it will continue shaking for billions more. Every time it quakes, it's a reminder that this supposedly dead world is more active and more mysterious than we ever imagined. Now, let's talk about something even more surprising. The moon might still have active volcanoes. Not massive eruptions like Earth's volcanoes, not towering mountains spewing lava into space, but subtle, localized volcanic activity that's happening right now on a world we thought went cold billions of years ago. For most of the 20th century, scientists believed the moon's volcanic activity ended roughly 3 billion years ago. The evidence seemed clear and convincing. The Lunar Maria, those dark plains visible from Earth, are solidified lava flows. When you look at the moon with your naked eye, you can see these dark areas. Ancient cultures saw shapes in them. Some saw a face, the man in the moon. Others saw a rabbit or a woman or various other figures depending on their cultural traditions. But these aren't shadows or surface markings. They're actually different terrain, fundamentally different from the bright lunar highlands. The Maria, Latin for seas, because early astronomers thought they might be actual bodies of water, are vast plains of basaltic lava. Basalt is a dark, dense volcanic rock, the same kind of rock that makes up much of the ocean floor on Earth, and that erupts from volcanoes like those in Hawaii. The Lunar Maria formed when lava erupted from the moon's interior, flooded low-lying regions, and then cooled and solidified. These lava flows were enormous. Mare Imbrium, the largest of the near-side Maria, covers an area of about 330,000 square miles. That's roughly the size of Texas and Alaska combined. Imagine lava flowing across an area that large, filling it to depths of hundreds of feet in some places. The volume of lava involved is staggering, hundreds of thousands of cubic miles of molten rock. Astronauts and robotic missions have sampled these Maria. Apollo 11 landed in Mare Tranquillitatis, the Sea of Tranquility. Apollo 12 landed in Oceanus Procellarum, the Ocean of Storms. The astronauts collected rocks from these lava plains and brought them back to Earth. Scientists analyzed these samples using radiometric dating, a technique that measures the decay of radioactive elements in rocks to determine their age. The Maria samples showed ages between about 3.9 and 3 billion years ago. Different Maria have slightly different ages. The older ones formed around 3.9 billion years ago, during or shortly after a period called the Late Heavy Bombardment. The younger ones formed around 3 billion years ago, possibly as late as 2.8 billion years ago in some locations. After that, the volcanic activity apparently stopped. No samples collected by Apollo missions showed ages younger than about 3 billion years. The conclusion seemed inescapable. The Moon had a period of intense volcanic activity between about 4 billion and 3 billion years ago, and then the eruptions ceased. The Moon's interior cooled, solidified, and the magma source shut off. For 3 billion years, the Moon has been volcanically dead, or so we thought. But starting in the 21st century, new observations challenged this timeline, and they did so in ways that were impossible to ignore. In 2014, data from NASA's Lunar Reconnaissance Orbiter revealed something unexpected that would force scientists to reconsider the entire history of lunar volcanism. But starting in the 21st century, new observations challenged this timeline. In 2014, data from NASA's Lunar Reconnaissance Orbiter revealed something unexpected. Scientists analyzing high-resolution images found dozens of small volcanic features that appeared to be much younger than the ancient Maria. These features are called irregular mare patches, or IMPs. They're small, rough-textured deposits, typically only a few hundred feet to a few miles across, sitting on top of the smooth Maria surfaces. They stand out because their texture is different, rougher and blockier than the surrounding ancient lava. IMPs have far fewer impact craters on them than the surrounding terrain. On the Moon, crater counting is a primary method for determining the age of surface features. The older a surface is, the more time it's had to accumulate impact craters. A surface with very few craters is young. The IMPs have so few craters that some appear to be less than 100 million years old. A few might be as young as 10 million years old. That's incredibly recent in lunar terms. 10 million years ago, Earth was in the Miocene epoch. Early apes were evolving, grasses were spreading across continents, and the Moon, supposedly long dead, might have been quietly erupting small amounts of lava. One of the most studied IMPs is a feature called Ina. Ina is a small depression, about 2 miles across, located in a region called Lacus Felicitatis. Inside Ina are rough, blocky mounds of material that look completely different from the smooth mare surface surrounding it. When scientists analyzed images of Ina, they realized the mounds have almost no impact craters. The original estimates suggested Ina might be less than 10 million years old. More recent analysis suggests it could be between 33 and 58 million years old, still remarkably young. What could create such young volcanic features? There are a few possibilities. One is that the Moon's interior is not as cold as we thought. Perhaps there are localized regions deep in the mantle that are still hot enough to melt rock. If magma from these regions can find a pathway to the surface, it could erupt, creating small lava flows. These wouldn't be massive eruptions, nothing like the ancient Maria-forming eruptions that covered vast areas. They'd be small, brief events, maybe only releasing a few cubic miles of lava. But even small eruptions would be astonishing on a world that's supposed to be volcanically dead. Another possibility is that the IMPs aren't volcanic at all, but are instead formed by some other process. Some researchers have suggested they could be created by the expansion of gases trapped beneath the surface. If pockets of gas build up pressure and then escape, they could disturb the surface, creating the rough, textured deposits we see. This would be a type of volcanic activity in the broad sense, involving the release of volatiles from the interior, but not traditional lava eruptions. There's also been speculation that IMPs could be related to moonquakes. If a strong, shallow moonquake fractures the surface, it might expose fresh material from beneath the dusty regolith, making it appear younger and rougher. But this doesn't fully explain the lack of impact craters, and it doesn't explain why these features are localized to specific areas. Then, there's the connection to transient lunar phenomena. Remember, many TLP observations have occurred in volcanic regions, including near features like the crater Aristarchus and the region around Ina. If small-scale volcanic activity is ongoing, it might explain some of the mysterious glows and flashes. Volcanic gases escaping from the surface could glow when ionized by solar radiation. Lava exposed briefly before cooling and solidifying could produce temporary brightening. Electrostatic effects from gas releases could levitate dust, creating obscurations. A connection between recent volcanic activity and TLPs would tie together several of the Moon's mysteries. It would explain why TLPs occur more frequently at certain locations, the locations where volcanic activity is most recent or ongoing. It would explain the spectroscopic detections of gases during some TLP events. It would provide a mechanism for the flashes and glows that have puzzled observers for centuries. NASA's Grail mission, which operated from 2011 to 2012, provided additional evidence that the Moon's interior might still be partially molten. Grail consisted of 2 spacecraft flying in formation around the Moon, precisely measuring variations in the Moon's gravitational field. These measurements allowed scientists to map the Moon's internal structure in detail. The data suggested that the Moon has a partially molten layer at the boundary between the mantle and the core, roughly 600 to 900 miles below the surface. This layer isn't a vast ocean of magma, but it's enough to indicate that the Moon's deep interior hasn't completely solidified. If parts of the Moon's interior are still molten, it's at least plausible that magma could occasionally make its way to the surface, especially if tectonic stresses create fractures that provide pathways. China's Chang'e 5 mission, which returned samples from the Moon in 2020, found volcanic rocks that dated to about 2 billion years ago. This was younger than the samples returned by Apollo missions, confirming that volcanic activity on the Moon continued longer than previously thought. 2 billion years ago is still ancient. It's half the age of the solar system, but it's 1 billion years more recent than the 3 billion-year-old Maria samples. The timeline of lunar volcanism keeps getting extended as we find younger and younger volcanic deposits. If the trend continues, it's not impossible that we'll eventually find definitive evidence of volcanic eruptions within the last few million years, or even more recently. The idea that the Moon might still be volcanically active, even in a very limited way, is profoundly strange. We're used to thinking of volcanic worlds as large and geologically vigorous, like Earth, with its hundreds of active volcanoes, or Io, Jupiter's moon, which is the most volcanically active body in the solar system. The Moon is small, only about 1/4 Earth's diameter. Small bodies cool quickly and go geologically dead. That's the rule we've learned from studying the solar system. Mars, larger than the Moon but smaller than Earth, had extensive volcanic activity billions of years ago, but appears to have largely stopped. Mercury, similar in size to the Moon, shows no evidence of recent volcanism. The Moon, by all rights, should be completely cold and inactive. Yet here we have evidence suggesting otherwise. Features that appear too young to fit the standard model. Seismic activity indicating a partially warm interior. Mysterious surface phenomena that might be linked to outgassing or minor eruptions. All of this points toward a Moon that's more dynamic, more active, more alive in a geological sense than we thought possible. And this brings us to another piece of the puzzle: the gases escaping from the Moon's interior. Let's talk about something invisible but revealing. The Moon is releasing gas, not constantly, not in massive quantities, but measurably and mysteriously. The Moon's tenuous exosphere, a trillion times thinner than Earth's atmosphere, contains atoms and molecules that have escaped from the lunar surface or interior. And some of those molecules are telling us that the Moon's interior is not as sealed and inactive as we once believed. The Apollo missions provided the first direct evidence of lunar outgassing. Several Apollo missions carried instruments designed to detect radon, a radioactive gas that forms from the decay of uranium and thorium in rocks. On Earth, radon seeps out of the ground in certain areas, and prolonged exposure can be a health hazard. On the Moon, radon would be extremely dilute and wouldn't pose a danger to astronauts, but detecting it would prove that gases are escaping from the lunar interior. And that's exactly what the Apollo instruments found. They detected radon-222, an isotope of radon with a half-life of about 3.8 days. The presence of radon-222 in the lunar exosphere means it must have been released from the interior relatively recently. If it had been sitting on the surface for weeks or months, it would have decayed away. The fact that it's detectable means it's being actively replenished, continuously seeping out from beneath the surface. This was early evidence that the Moon is not a sealed ball of rock. There are pathways, cracks, or fissures through which gases can escape from the interior to the surface and into the exosphere. More recently, NASA's LADEE mission, which orbited the Moon from 2013 to 2014, detected argon-40 in the lunar exosphere. Argon-40 is another noble gas produced by the radioactive decay of potassium-40 in rocks. LADEE's instruments were sensitive enough to measure variations in argon-40 concentration, and what they found was fascinating. The amount of argon-40 in the exosphere changes over time. Sometimes it increases, sometimes it decreases. The variations appear to be correlated with the Moon's position in its orbit. When the Moon is at perigee, closest to Earth, the argon-40 concentration tends to increase. This suggests that tidal stresses, the same stresses that trigger deep moonquakes, might also be enhancing gas release. When Earth's gravity squeezes the Moon, it opens or widens cracks in the crust, allowing trapped gases to escape more easily. This is direct evidence of a connection between tidal forces, moonquakes, and outgassing. All three phenomena are related, all driven by the ongoing tidal interaction between Earth and the Moon. The presence of outgassing also provides a plausible explanation for some transient lunar phenomena. When gas escapes from the Moon's interior and reaches the surface, several things can happen. If the gas is ionized by solar ultraviolet radiation, it will glow. Different gases glow in different colors depending on their composition. This could explain the colored glows reported in TLP observations. If the gas release is sudden and forceful, it could kick up dust from the surface, creating a temporary cloud that obscures or alters the appearance of that area. This could explain the obscuration-type TLPs, where parts of the moon temporarily become hazy or less distinct. If the gas contains volatile compounds, they might freeze upon reaching the cold lunar night, creating temporary frost deposits that alter the reflectivity of the surface. These deposits would sublimate away when sunlight returns, making the effect temporary. The outgassing also tells us something important about the moon's interior composition. For gases like radon and argon to be present, the moon's interior must contain radioactive elements like uranium, thorium, and potassium. These elements are concentrated in certain types of rocks, particularly in the crust and upper mantle. The fact that we detect their decay products escaping from the moon confirms that the moon's interior has a composition similar to what we expected based on Apollo samples. But it also shows that the interior is not completely isolated from the surface. There are connections, pathways for gas to migrate upward. This has implications for understanding the moon's thermal evolution. Radioactive decay generates heat. Uranium, thorium, and potassium, collectively known as heat-producing elements, have been generating heat inside the moon for billions of years. This radioactive heat is one reason the moon's interior hasn't cooled as quickly as simple models predicted. Even though the moon is small and should cool rapidly, the ongoing radioactive decay provides a continuous internal heat source. Over billions of years, this heat has kept parts of the interior warm enough to remain partially molten, or at least ductile. Some researchers have speculated that outgassing events might be linked to moonquakes. If a moonquake fractures rock in the lunar crust or mantle, it could open new pathways for trapped gases to escape. You'd expect to see a temporary increase in outgassing shortly after a strong moonquake. This hasn't been definitively observed yet, because we don't have continuous monitoring of both moonquakes and outgassing. But future missions might be able to test this hypothesis. The Lady mission also detected sporadic bursts of larger particles in the lunar exosphere, possibly dust grains. These bursts seem to correlate with times when Earth is passing through meteoroid streams, like the Geminids or Perseids. When meteoroids hit the moon, they vaporize a small amount of surface material and kick up dust. This dust can be detected by orbiting spacecraft. But some of the particle bursts detected by LADY didn't correlate with known meteoroid streams, suggesting they might be caused by internal processes. Possibly gas releases strong enough to loft dust particles. There's still much we don't understand about lunar outgassing. What controls the rate of gas release? Why are some areas more active than others? How much gas is being lost over time, and how does this affect the moon's long-term evolution? Future missions will need to deploy instruments on the surface to monitor outgassing in real time, measuring the composition and flux of gases at different locations, and correlating these measurements with moonquakes, tidal forces, and surface phenomena. The moon is not a sealed vault. It breathes, in a sense, releasing gases from its interior in response to stresses and temperature changes. This outgassing is subtle, far less dramatic than volcanic eruptions on Earth or geysers on Saturn's moon Enceladus. But it's real, and it's ongoing, another sign that the moon is more active than we once thought. Now let's turn to one of the moon's strangest features: magnetic anomalies. The moon has no global magnetic field like Earth's. Earth's magnetic field is generated by a dynamo in the planet's liquid iron core. Electric currents flowing in the molten metal create a magnetic field that extends far into space, protecting us from solar wind and cosmic radiation. The moon, being much smaller and cooler, has no active dynamo. Its core is solid, or at most only partially molten, and too small to generate a global magnetic field. When Apollo astronauts measured the Moon's magnetic field, they confirmed this. There's no dipole field like Earth's, no lunar version of the north and south magnetic poles. But what they also discovered was completely unexpected. There are localized magnetic anomalies scattered across the Moon's surface, regions where the magnetic field is much stronger than the surrounding areas, sometimes hundreds of times stronger. These magnetic anomalies are small, typically only a few miles across, but the magnetic fields they produce are strong enough to be measured from orbit and even strong enough to deflect the solar wind. How can a world with no global magnetic field have these intense local magnetic fields? The answer seems to be that the Moon once had a global magnetic field billions of years ago, but it shut down when the lunar core stopped generating a dynamo. This is one of the most important discoveries about the Moon's history, and it completely changed how we think about small planetary bodies. Before we understood the Moon's magnetic history, scientists assumed that only large planets could generate magnetic fields. Earth has a magnetic field because it's large enough to have retained a hot, liquid iron core. The core is roughly the size of Mars, a ball of molten metal about 4,300 miles in diameter. Convection currents in this liquid metal generate electric currents, and those electric currents create Earth's magnetic field. This process is called a dynamo, and it's been operating for at least 3 billion years, probably longer. Mercury, the smallest planet, has a weak magnetic field, suggesting it still has a partially molten core despite its small size. Venus and Mars, both smaller than Earth, have no significant global magnetic fields today. Venus may never have had one, or if it did, it shut down billions of years ago and left no clear evidence. Mars had a magnetic field early in its history. We know this because Martian rocks in some regions show remnant magnetization. But the Martian dynamo shut down roughly 4 billion years ago when the planet's core cooled and solidified. The Moon is much smaller than Mars, only about half the diameter and about 1/8 the mass. Nobody expected the Moon to ever have had a dynamo. It should have cooled too quickly. But the magnetic anomalies proved that assumption wrong. Before the dynamo stopped, certain rocks on the Moon's surface became magnetized, permanently recording the ancient field. Here's how that works. When lava erupts and flows across the surface, it's extremely hot, well over 2,000 degrees Fahrenheit. At these temperatures, the atoms in the rock are moving so vigorously that they can't hold a magnetic alignment. The rock is essentially magnetically scrambled, but as the lava cools, it eventually drops below a critical temperature called the Curie temperature, named after Pierre Curie, who discovered the phenomenon. For iron-bearing minerals, the Curie temperature is around 1,000 degrees Fahrenheit, though it varies depending on the exact composition. Below the Curie temperature, magnetic domains in the rock can align with any external magnetic field. If there's a magnetic field present, when the rock cools through the Curie temperature, the rock becomes permanently magnetized in the direction of that field. This is called thermormanent magnetization. The magnetization is locked in place and remains even after the external field disappears. On Earth, this process has recorded millions of years of magnetic field history in rocks. By studying the magnetization of ancient lava flows, scientists have discovered that Earth's magnetic field has flipped many times, with north and south magnetic poles reversing positions. The last flip happened about 770,000 years ago. Before that, Flips occurred every few 100,000 years on average. The rock record shows all of these reversals, preserved in the magnetic minerals. The same process happened on the Moon, but on a smaller scale and in a more limited time window. When lunar lava flows erupted and cooled in the presence of the Moon's ancient magnetic field, they became magnetized. Even after the global field disappeared, the rocks retained their magnetization, creating the anomalies we see today, billions of years later. This tells us something profound about the Moon's history and raises deep questions about how small bodies evolve. The Moon must have had a liquid, convecting core early in its history, generating a magnetic field strong enough to magnetize surface rocks. The field strength appears to have been comparable to Earth's field, possibly even stronger in some periods. Estimates based on the strength of the remnant magnetization suggest the ancient lunar field was somewhere between 10 and 100 microteslas. Earth's current field at the surface is about 50 microteslas, so the lunar field was in the same ballpark. This field lasted for at least several 100 million years, possibly longer, before the core cooled and solidified, shutting down the dynamo. The timing of when the lunar dynamo operated is still debated among scientists, and it's an active area of research. Some evidence suggests the dynamo was active from about 4.2 billion years ago to around 3.5 billion years ago. That's a span of 700 million years, longer than the entire history of complex life on Earth. Other evidence suggests it might have lasted even longer, perhaps continuing until as recently as 3 billion years ago, or even later. The debate centers on how to interpret the magnetic signatures in different lunar samples. Some samples show strong magnetization, indicating they formed when a powerful magnetic field was present. Other samples show weak or no magnetization, suggesting they formed after the field had weakened or shut down. By carefully dating these samples and measuring their magnetic properties, scientists are trying to piece together a timeline of how the lunar magnetic field evolved. What's clear is that the Moon was more geologically active in its early history than anyone expected. A small body like the Moon shouldn't have been able to sustain a dynamo for that long. Earth has maintained its dynamo for over 3 billion years because Earth is large and retains heat well. The Moon should have cooled too quickly to keep its core molten for hundreds of millions of years. Yet the magnetic evidence says otherwise. One possibility is that the Moon's core was heated by tidal interactions with Earth. In the Moon's early history, it was much closer to Earth than it is now, and the tidal forces were correspondingly stronger. These forces could have generated enough internal friction and heating to keep the core molten longer than it would have stayed molten otherwise. Eventually, as the Moon drifted farther from Earth and tidal heating decreased, the core cooled and the dynamo shut down. The magnetic anomalies also have another strange feature. Many of them are associated with bright swirls on the lunar surface. These swirls are sinuous, looping patterns of bright and dark material that look almost like someone painted them on the Moon with a brush. They're visible in photographs from orbit, standing out against the darker surrounding terrain. The most famous swirl is called Rhina Gamma, located in Oceanus Procellarum. Rhina Gamma is a bright, irregularly shaped feature about 30 miles across. It's not a crater or a lava flow or any conventional geological feature. It's just a pattern of bright material on the surface. And it's directly associated with one of the strongest magnetic anomalies on the Moon. Scientists have discovered that these swirls form in regions where the magnetic field is strong enough to deflect the solar wind. The solar wind is a stream of charged particles, mostly electrons and protons, flowing from the sun. These particles constantly bombard the moon's surface, and over time, they cause a process called space weathering. The particles break down minerals on the surface, darkening them and changing their color. But in areas protected by a magnetic field, the solar wind particles are deflected away. The surface doesn't darken as quickly, so it remains brighter than the surrounding terrain. Over millions of years, this creates the swirl patterns we see. The bright areas are magnetically shielded. The dark areas are not. This is a remarkable example of how invisible magnetic fields can shape visible surface features. The swirls are essentially magnetic shadows, regions protected from space weathering by ancient magnetic fields frozen into the lunar crust. These magnetic anomalies might also have a connection to transient lunar phenomena. If magnetic fields are strong enough to deflect solar wind, they might also influence how dust behaves on the surface. Charged dust particles could be affected by the magnetic fields, potentially becoming electrostatically levitated more easily in these regions. If so, areas with strong magnetic anomalies might be more prone to dust-related TLPs. This is speculative, and more research is needed, but it's an intriguing possibility. There's another mystery related to the magnetic anomalies. Some of them are located at points on the moon's surface that are directly opposite major impact basins. For example, there's a cluster of magnetic anomalies on the far side of the moon, directly opposite the Imbrium Basin on the near side. The Imbrium Basin is a huge impact crater, over 700 miles across, formed by a massive asteroid impact billions of years ago. How could an impact on one side of the moon create magnetic anomalies on the opposite side? One hypothesis is that when the giant asteroid hit, it sent seismic waves traveling through the moon's interior. These waves converged at the point directly opposite the impact, called the antipode. The converging seismic waves created enormous pressures and temperatures at the antipode, possibly enough to melt rock and create a temporary zone of intense activity. If the moon still had an active dynamo at the time, the molten rock at the antipode could have become strongly magnetized. When it cooled, it retained that magnetization, creating the anomalies we see today. This hypothesis is supported by the fact that the antipodal magnetic anomalies tend to be clustered in rough, disrupted terrain, exactly what you'd expect if seismic focusing had disturbed the surface. Understanding the moon's magnetic anomalies is important for future exploration. If astronauts are going to spend extended periods on the moon, they'll be exposed to radiation from the solar wind and cosmic rays. Earth's magnetic field provides significant protection from this radiation, reducing exposure by deflecting charged particles. The moon has no such protection, except in regions with strong local magnetic anomalies. It's possible that future lunar bases could be intentionally located in magnetically shielded regions to reduce radiation exposure. Astronauts living in these areas would receive less radiation than those in unshielded areas. It wouldn't be perfect protection. Magnetic fields strong enough to deflect cosmic rays would need to be far stronger than what exists on the moon. But even partial shielding could reduce cumulative radiation doses, making long-term lunar habitations safer. The magnetic anomalies are remnants of the moon's ancient past, frozen records of a time when the moon had a global magnetic field and was geologically vibrant. They remind us that the moon's history is more complex than we once thought. This small, supposedly simple world had an active core, a magnetic dynamo, and a dynamic interior for hundreds of millions of years. And even though the dynamo shut down billions of years ago, Its effects are still visible and measurable today, influencing how the surface weathers and possibly affecting ongoing phenomena like TLPs. Finally, let's talk about something that's both measurable and inevitable. The moon is leaving us. Not quickly, not dramatically, but steadily and permanently. Every year, the moon moves about 1.5 inches farther from Earth. That's roughly 3.8 centimeters per year. At that rate, over 1 million years, the moon will have receded about 24 miles. Over 100 million years, about 2,400 miles. These are tiny distances compared to the current Earth-Moon separation of about 240,000 miles, but they add up over geological time. And the process is accelerating, very slowly, but measurably. We know the moon is moving away because we can measure it directly. During the Apollo missions, astronauts placed retroreflector arrays on the moon's surface. These are panels covered with special mirrors designed to reflect laser light back toward its source. Since the 1970s, scientists have been firing laser pulses from Earth-based telescopes toward these retroreflectors. The laser light travels to the moon, bounces off the retroreflector, and returns to Earth. By measuring the round-trip travel time of the laser pulse with extreme precision, scientists can calculate the exact distance to the moon at that moment. These measurements are astonishingly accurate, precise to within a few millimeters. Over decades of repeated measurements, the data clearly shows that the moon is gradually moving farther away. The recession rate is about 1.5 inches per year, or 3.8 centimeters per year. This has been confirmed by multiple observatories using different retroreflectors, so there's no doubt about it. The moon is definitely receding. But why? The answer lies in tides. Not just the ocean tides that we see on Earth's beaches, but the tidal interaction between Earth and the moon that transfers energy and angular momentum. Here's how it works. The moon's gravity pulls on Earth, creating bulges in Earth's oceans. There are two bulges, one on the side of Earth facing the moon, and one on the opposite side. As Earth rotates, these bulges move around the planet, creating the high and low tides that coastal areas experience twice a day. But there's a complication. Earth rotates faster than the moon orbits. A day on Earth is 24 hours. The moon's orbital period is about 27.3 days. Because Earth rotates faster, the tidal bulges don't stay perfectly aligned with the moon. Friction between the moving water and the ocean floor causes the bulges to be dragged ahead of the moon's position. The bulge facing the moon is slightly ahead of where the moon actually is. This misaligned bulge has its own gravity, and it pulls on the moon. The gravitational pull from the bulge accelerates the moon in its orbit, giving it more energy. When an object in orbit gains energy, it moves to a higher orbit, farther from the object it's orbiting. That's basic orbital mechanics. So the moon, gaining energy from Earth's tides, gradually spirals outward. At the same time, the tidal interaction is slowing Earth's rotation. The moon's gravity pulls back on the tidal bulge, creating a torque that acts like a brake on Earth's spin. Over time, this slows Earth's rotation, making each day slightly longer. The day is currently lengthening by about 1.7 milliseconds per century. That's a tiny effect, far too small to notice in a human lifetime. But over millions of years, it adds up. 500 million years ago, a day on Earth was only about 22 hours long. 1 billion years ago, a day might have been 18 hours. Go back far enough, and days were even shorter. This has been confirmed by studying ancient fossils, particularly corals and other organisms that grow in layers. Each layer corresponds to a day, and by counting the layers in a year's worth of growth, scientists can determine how many days were in a year at that time. Fewer days per year means shorter days. The data matches the predictions from tidal models. Earth's rotation is slowing, and it's slowing because of the Moon. The Moon is also transferring angular momentum to Earth's orbit around the Sun, but the dominant effect is the recession of the Moon and the slowing of Earth's rotation. Eventually, billions of years in the future, Earth and the Moon will reach a state called tidal locking. In this configuration, Earth's rotation will slow down enough that the same side of Earth always faces the Moon. This is already true for the Moon. The Moon is tidally locked to Earth, which is why we always see the same face of the Moon from Earth. The Moon rotates once per orbit, so the same hemisphere always points toward us. When Earth becomes tidally locked to the Moon, one side of Earth will always face the Moon, and the Moon will hang stationary in the sky, as seen from that hemisphere. From the other side of Earth, the Moon will never be visible. It will always be below the horizon. This won't happen for billions of years, and by that time, the Sun will have evolved into a red giant, likely rendering the question moot. But the process is already underway. The Moon is slowly leaving, and Earth's rotation is slowly decreasing. The recession of the Moon has profound implications for Earth's climate and environment, and the effects go far beyond just having smaller tides. The Moon stabilizes Earth's axial tilt, and this might be one of the most important factors in making Earth habitable. Earth's axis is currently tilted about 23.5 degrees relative to its orbital plane around the Sun. This tilt is called obliquity, and it's responsible for the seasons. When the northern hemisphere is tilted toward the Sun, it's summer in the north and winter in the south. 6 months later, when the northern hemisphere is tilted away from the Sun, it's winter in the north and summer in the south. The tilt remains constant throughout the year as Earth orbits the Sun. Earth doesn't wobble or flip as it moves through space. The axis points in the same direction, toward the star Polaris, the North Star, which is why that star appears stationary in the northern sky, while other stars rotate around it. This stability is crucial for maintaining a stable climate. If Earth's tilt changed significantly, the seasons would change. A larger tilt would mean more extreme seasons, hotter summers, and colder winters. A smaller tilt would mean milder seasons, with less temperature variation between summer and winter. Without the Moon's gravitational influence, Earth's axial tilt would vary chaotically over millions of years, and the consequences for climate would be severe. Mars provides a cautionary example of what happens to a planet without a large, stabilizing moon. Mars has 2 tiny moons, Phobos and Deimos, but they're essentially captured asteroids, far too small to have any significant gravitational influence on Mars's axial tilt. Phobos is only about 14 miles across. Deimos is even smaller, only about 8 miles across. These are pebbles compared to Earth's moon, which is over 2,000 miles in diameter. Without a large moon to stabilize it, Mars's axial tilt has varied wildly over its history. Computer simulations and analysis of Martian geological features suggest that Mars's tilt has swung from as low as about 10 degrees to as high as 60 degrees or more. Currently, Mars' tilt is about 25 degrees, similar to Earth's, but that's just a temporary state. Over the next few million years, it will change significantly. These variations in tilt cause dramatic climate changes on Mars. When the tilt is low, the polar regions receive very little sunlight. They become extremely cold, and carbon dioxide and water freeze out of the thin atmosphere, accumulating as ice at the poles. The atmospheric pressure drops because so much of the atmosphere is frozen out. When the tilt is high, the polar regions receive much more sunlight. The ice caps warm up and release carbon dioxide and water vapor back into the atmosphere. The atmospheric pressure increases, and the climate changes dramatically. Some geological features on Mars, including gullies and layered deposits, appear to have formed during these high obliquity periods when the climate was very different from today. Earth, thanks to the Moon, has avoided this kind of chaotic climate variation. For hundreds of millions of years, Earth's tilt has remained close to 23.5 degrees. It does vary slightly, between about 22.1 and 24.5 degrees. But these variations happen slowly over a cycle of about 41,000 years. This slow, regular variation is one of the Milankovitch cycles that contribute to ice ages, but it's predictable and relatively gentle. The climate changes, but not catastrophically. Life has time to adapt. If Earth's tilt varied as wildly as Mars, the consequences would be catastrophic for complex life. Imagine if Earth's axial tilt suddenly increased to 60 degrees over a few million years. The polar regions would receive far more sunlight during summer, potentially melting all polar ice. Tropical regions would receive less consistent sunlight and might cool down. The entire atmospheric circulation pattern would change. Weather systems would be completely different. Ocean currents would shift. Ecosystems adapted to current conditions would collapse. Then, a few million years later, the tilt might swing back to 10 degrees, creating entirely different but equally dramatic changes. Complex life forms, particularly large animals, with long generation times and specific habitat requirements, would struggle to adapt to such rapid and unpredictable changes. The Moon prevents this by acting as a gravitational anchor, keeping Earth's tilt stable. The Moon's gravity creates a torque on Earth's equatorial bulge, the slight thickening around the equator caused by Earth's rotation. This torque acts like a gyroscope, resisting changes to Earth's orientation. The result is that Earth's axis precesses, tracing out a slow circle in space over about 26,000 years, but the tilt angle itself remains nearly constant. This stability has allowed complex life to evolve and thrive. The seasons change in a predictable pattern. Climate zones remain relatively stable over long periods. Life can adapt to slow, gradual changes rather than facing chaotic, unpredictable swings. Some scientists argue that the Moon's stabilizing influence was essential for the evolution of complex life on Earth, and that planets without large moons might be less likely to develop complex ecosystems. This is speculative, and there's debate about how important this factor really is. But it's certainly plausible that climate stability matters for the evolution of complex life. But the Moon isn't going to disappear suddenly. Its recession is gradual, and Earth's axial tilt will remain stable for billions of years. By the time the Moon has moved far enough away to lose its stabilizing effect, the Sun will have already made Earth uninhabitable. The Moon's recession also affects tides. As the Moon moves farther away, its gravitational pull on Earth weakens. Weaker tidal forces mean smaller tides. Eventually, ocean tides will be significantly reduced. This will have effects on coastal ecosystems that depend on tidal zones on ocean circulation patterns, and on the mixing of nutrients in coastal waters. Again, these effects will take millions of years to become significant. There's another fascinating aspect to the Moon's recession. If we extrapolate backward in time, we can calculate where the Moon was in the past. 4 billion years ago, the Moon was much closer to Earth, perhaps only about 15,000 miles away, compared to the current 240,000 miles. At that distance, the Moon would have appeared enormous in Earth's sky, more than 10 times larger in angular diameter than it appears today. Tides would have been colossal, with tidal forces hundreds of times stronger than today. Ocean tides would have risen hundreds of feet, inundating coastlines twice a day. The tidal heating from these extreme forces would have kept Earth's interior molten and geologically active. Earth's rotation would have been much faster, with days lasting only 5 or 6 hours. This early Earth-Moon system would have been dramatically different from what we experience today. Over billions of years, tidal interactions have gradually transformed the system into the configuration we see now, with the Moon far away and Earth rotating slowly. The Moon's recession is a reminder that nothing in the solar system is static. Objects move, orbits change, systems evolve. The Earth-Moon system we have today is a snapshot in a long, slow transformation that began billions of years ago and will continue for billions more. The Moon we see tonight is farther from Earth than the Moon our ancestors saw 1 million years ago. The Moon our distant descendants will see, if any humans are still around, will be farther still. The Moon is leaving, slowly but inexorably, driven by the same tidal forces that create the ebb and flow of Earth's oceans. Tonight we've explored a Moon that's nothing like the dead, unchanging rock we thought we knew. We've seen that the Moon flashes with mysterious lights that have puzzled observers for centuries, phenomena we still don't fully understand. We've learned that the Moon is shrinking as its interior cools, creating thousands of young fault scarps that reveal ongoing tectonic activity. We've discovered that the Moon contains water, not just in permanently shadowed craters, but even on the sunlit surface, a finding that transforms our plans for future exploration. We've found that the Moon shakes with moonquakes, some occurring deep in the mantle where a cold, dead world shouldn't produce any seismic activity at all. We've encountered evidence that the Moon might still have limited volcanic activity, with features so young they could have formed within the last few million years. We've detected gases escaping from the Moon's interior, radon and argon seeping out through cracks in the crust, proving that the interior is not sealed and inactive. We've explored the Moon's strange magnetic anomalies and the beautiful swirl patterns they create, remnants of an ancient magnetic field that once protected the lunar surface. And we've measured the Moon's gradual recession from Earth, a process that's been happening for billions of years and will continue for billions more. Each of these discoveries contradicts what we thought we knew. The Moon we were taught about in school, the Moon of old textbooks and outdated assumptions, was simple and boring. A grey ball of rock, geologically dead, with nothing happening on or below its surface. That Moon doesn't exist. The real Moon is active. It's evolving. It's releasing energy and matter. It's responding to forces and processes we're still working to understand. Some of these processes are clearly linked. The Moon's shrinking creates stress that triggers moonquakes. The moonquakes might open pathways for outgassing. The outgassing might produce the mysterious flashes we see as transient lunar phenomena. The tidal forces from Earth cause both moonquakes and gas releases. The ancient magnetic field created protective zones that still affect how the surface weathers today. Everything is connected in ways we're only beginning to understand. And there's still so much we don't know. We don't know exactly what causes all the different types of TLPs. We don't know whether the moon has had any volcanic eruptions in the last million years. We don't know how much heat remains in the moon's deep interior. We don't know the full extent of water deposits or how they're distributed. We don't know why some regions have strong magnetic anomalies while others don't. These mysteries are opportunities. Every unanswered question is a chance for future missions to make new discoveries. NASA's Artemis program plans to return humans to the moon within the next few years. Unlike Apollo, which was focused on getting there first and proving it could be done, Artemis is about establishing a permanent presence. Astronauts will live and work on the moon for extended periods. They'll deploy new scientific instruments, drill into the surface, explore permanently shadowed craters, and search for resources like water ice. China, India, Russia, and private companies are also planning lunar missions. We're entering a new era of lunar exploration, one that will be sustained and systematic rather than a brief sprint. And all of this activity will help us understand the strange phenomena we've discussed tonight. New seismometer networks will map moonquakes in detail, helping us understand the moon's internal structure and identify connections between quakes, tides, and outgassing. Instruments monitoring the exosphere will detect gas releases in real time, measuring their composition and correlating them with surface events. Cameras continuously observing the surface will capture TLPs as they happen, providing data on their frequency, distribution, and possible causes. Drilling into the lunar crust will retrieve samples from deeper layers, telling us about the moon's composition and thermal history. Robotic rovers will visit magnetic anomalies and swirl features, studying them up close and determining how they formed. Within our lifetimes, we might finally answer the questions that have puzzled astronomers for centuries. What causes the moon to flash? Is there ongoing volcanic activity? How active is the moon's interior? The moon is the only other world that humans have walked on. It's the closest celestial body to Earth, visible in our sky almost every night. It's been a companion to our planet for over 4 billion years, stabilizing our climate, creating tides, lighting the night. And yet, we're still discovering how strange and active it really is. That's the beauty of science. Even the most familiar objects can surprise us. Even the things we think we understand completely can reveal new mysteries when we look more closely. The moon looked the same to ancient civilizations as it does to us. They saw the same craters, the same Maria, the same bright highlands. But they didn't know it was shrinking. They didn't know it was shaking. They didn't know it contained water or released gases or had once possessed a magnetic field. We know these things now because we've built instruments sensitive enough to detect them and missions bold enough to go there and measure them directly. And we're not done. Every new mission reveals something unexpected. Every new dataset contains surprises. The moon we'll understand in 50 years will be different from the moon we understand now, just as our current understanding is radically different from what we knew 50 years ago. The moon is leaving us, moving farther away year by year. But before it gets too far, we're going back. We're going back to understand it, to use its resources, to learn its secrets. And maybe, just maybe, to answer the question that's been hanging over all these discoveries. If the moon, a small, supposedly dead world right next to Earth, is this active and surprising, what does that tell us about other worlds? How many other supposedly dead moons or planets in our solar system might be active in ways we haven't detected yet? What strange phenomena might be happening on distant moons we've barely studied? The moon has taught us to be humble, to question our assumptions, to look more closely at things we think we understand, and to appreciate that the universe is far stranger and more wonderful than we ever imagined. Something really strange is happening on the moon. And we're finally beginning to understand it. Thanks for staying with me through this journey. The next time you look up at the moon, remember what you've learned tonight. That grey sphere isn't a dead rock. It's an active world, shrinking and shaking, releasing gas and maybe even lava, holding water and ancient magnetic secrets. It's still surprising us after billions of years. And it will continue to surprise us for as long as we keep looking, keep exploring, keep questioning, keep looking up. The universe has more mysteries waiting to be uncovered, and the moon, our closest companion, has shown us that even the familiar can be endlessly fascinating.